Far beyond Pluto, far beyond the wide belt of known icy bodies, and far beyond the vast shell of distant comet reservoirs that still remain loosely bound to the Sun, interstellar space continues in a thin and quiet state. Matter is present, but only lightly. A few atoms drift through each cubic centimetre. Fine dust moves in sparse grains. Weak magnetic fields thread through this darkness. Starlight crosses the emptiness for years, centuries, and longer spans without meeting anything large enough to stop it. In this outer setting, a rogue planet travels alone. A rogue planet is a planet-sized world that does not orbit a star. Observations show that such bodies exist in the galaxy. Some are likely thrown out of young planetary systems during violent early reshuffling. Some may form in ways closer to small stars, gathering from a collapsing cloud but never becoming massive enough to ignite steady fusion in their cores. What matters here is simple. It is a world without a sun, moving through the Milky Way under the pull of the galaxy itself and the accumulated gravity of nearby stars and gas. Far beyond Pluto, far beyond the wide belt of known icy bodies, and far beyond the vast shell of distant comet reservoirs that still remain loosely bound to the Sun. Interstellar space continues in a thin and quiet state. Matter is present, but only lightly. Few atoms drift through each cubic centimetre. Fine dust moves in sparse grains. Weak magnetic fields thread through this darkness. Starlight crosses the emptiness for years, centuries, and longer spans without meeting anything large enough to stop it. In this outer setting, a rogue planet travels alone. A rogue planet is a planet-sized world that does not orbit a star. Observations show that such bodies exist in the galaxy. Some are likely thrown out of young planetary systems during violent early reshuffling. Some may form in ways closer to small stars, gathering from a collapsing cloud but never becoming massive enough to ignite steady fusion in their cores. What matters here is simple. It is a world without a sun, moving through the Milky Way under the pull of the galaxy itself and the accumulated gravity of nearby stars and gas. In this outermost region, before any effect reaches the solar system in a practical sense, the rogue planet remains first a moving mass, and only second a physical landscape. Its internal nature matters less than its gravity. It may be rocky like a super-Earth. It may be icy. It may be a gas giant with a deep atmosphere of hydrogen and helium. It may even carry faint internal heat, left over from formation, or produced slowly by radioactive decay in its interior. If it is large and young enough, that heat may support a dim glow in infrared light, too weak for human eyes, but present for sensitive instruments. If it is old and small, it may be almost invisible except when it passes in front of a star or bends light very slightly through gravity. In the deep dark between stars, such an object is difficult to find at great distance. The solar system seen from this far out is not a bright target. The Sun is still the dominant object, but at enormous distances its light shrinks toward the brightness of an ordinary star. The planets are hidden within that glow. Their reflected light is negligible. The entire system is less a shining structure than a gravitational domain spread through space, near its broadest edge. The Sun still holds sway over many icy bodies that can fall inward and return outward again on long journeys. Yet that outer hold is weak. It competes with passing stars, galactic tides, and the slow background forces of the Milky Way. The boundary is not a wall. It is a fading region where the Sun's influence becomes easier to disturb. The rogue planet enters this environment gradually, not by crossing a marked line, but by moving from one balance of gravity into another. At first, the Sun is only one pull among many. The galaxy sets the broad motion. Nearby stars, though distant, contribute small long-term effects. The rogue planet follows a path that from the Sun's point of view is an incoming interstellar trajectory. In ordinary terms, it is passing through rather than circling in. Unless it loses energy through a rare gravitational exchange, it does not simply settle into orbit. It approaches on a path that is usually open, not closed. This point matters because popular imagination often treats a wandering planet as if it can slip naturally into a stable place among the known planets. Orbital mechanics does not favour that result. To become permanently bound to the Sun, an incoming body must give away some of its motion energy. Empty space offers almost no way to do this. There is no thick gas to brake against. Sunlight pressure is far too weak. The usual mechanism would be a close gravitational interaction with another massive body, most likely one of the giant planets, or in more distant eras a richer environment of passing stars within the Sun's birth cluster. In the present solar system, permanent capture is possible in principle, but it is not the simplest expectation. The simplest expectation is passage through and then departure, with whatever disturbances the crossing causes. At this outer distance, however, nothing dramatic is visible yet. There is only approach. The rogue planet moves under inertia, meaning motion carried forward unless gravity changes it. Its speed relative to the Sun may be several kilometers per second, or more, depending on its origin and direction within the galaxy. That speed is large on human scales and modest on galactic scales. It means the crossing of the extreme outer solar system would still take a very long time, even after the body first enters the most distant region where the Sun's gravity begins to matter more than before. The journey inward unfolds over thousands to many tens of thousands of years. The process is not sudden. It is extended, quiet, and almost entirely beyond direct human sense. Its surface, if one could somehow remain nearby, reflects that long isolation. A rocky rogue planet would receive no steady daylight from a parent star. If it has no thick atmosphere and no strong internal heating, its outer layers would become extremely cold. Volatile substances such as water, methane, nitrogen, and carbon dioxide would freeze hard if present at the surface. An icy rogue planet would be darker still, its frozen crust altered slowly by cosmic rays, tiny impacts, and long exposure to the interstellar medium. A gas giant would differ. Deep within its atmosphere, heat from formation could remain trapped for billions of years. Flowing slowly outward, its cloud tops would still be frigid, but its overall brightness in infrared wavelengths could exceed that of a rocky world. None of these features change the gravitational story at this stage. They only shape how detectable the world might be. Detection from the inner solar system would remain difficult while the object stays this far out. Astronomers could in principle notice a faint moving source in infrared surveys if the planet were large enough, warm enough, or close enough. They might also infer its presence indirectly through subtle disturbances in distant comet orbits, though at the earlier stage those effects would be too small and too slow to stand out clearly. The sky is crowded with faint sources. Slow motion against the stars can take years to separate from noise and uncertainty. Discovery would therefore depend on mass, distance, brightness, direction, and patient observation, rather than on any immediate sign in the inner planetary system. So the opening state remains calm. Interstellar space does not announce the intruder. The outer solar system does not yet flash or crack. The Sun continues to shine in its ordinary way. The known planets continue their long-established paths. But in the far dark, beyond the region where sunlight gives any warmth, and beyond the crowded architecture of the major planets, a free world enters the broad outer field of the Sun. It carries its own mass, its own momentum, its own history of ejection or isolated formation. Its arrival begins not with collision, noise, or visible upheaval, but with a change in gravitational bookkeeping. One more significant body is now part of the calculation. In this remote region, that is how the event begins. The outer Oort cloud is not a ring and not a flat belt. It is better understood as a vast spherical reservoir of icy bodies surrounding the solar system on all sides, extending across distances so large that ordinary planetary scales lose their usefulness. These objects are thought to be leftovers from the early formation of the solar system, scattered outward long ago by the giant planets and then lifted into distant, weakly bound paths by passing stars and the tidal pull of the Milky Way. In this far domain, the Sun is still the central mass, but its grip is light. Each icy body belongs to the solar system in a technical sense, yet many of them move along enormous orbits that are only loosely held together. A rogue planet entering this region does not arrive in a crowded place. The cloud contains a great many objects, but the space between them is immense. There is no dense swarm, no shining shell, no close-packed field of ice. The dominant effect here is not collision, it is disturbance by gravity. The rogue planet brings with it a moving gravitational field, and in a region where bodies are weakly bound and widely spread, even modest changes in gravitational conditions can matter over very long spans. The first changes are subtle. A single icy body in the outer Oort cloud follows a slow path around the Sun, often taking millions of years to complete one circuit. Its orbit can be tipped in almost any direction. Its speed is low, its relation to the Sun is delicate. This means that a passing mass does not need to strike it, or even come very close on planetary scales, to alter its future. A small change in speed or direction in this outer region can grow into a large difference over time. The path may become slightly more elongated. Its closest future approach to the Sun may move inward or outward. Its orbital plane may tilt. In some cases, the object may be loosened enough to leave the Sun's influence entirely. In others, it may become more tightly aimed toward the inner system, though not immediately and not in a neat wave. This is how the disturbance begins across the cloud, not as a visible front, and not as a single event, but as a widening set of altered trajectories. The rogue planet passes through one part of the outer reservoir, and nearby icy bodies respond first. Those a little farther away respond less strongly. Others remain almost unchanged. The result is patchy. Some orbital families are disturbed, others are barely touched. If the rogue planet is massive, the affected volume becomes larger. If it is less massive, the changes are more local. Distance matters greatly. Gravity weakens with separation, so the strongest effects belong to the nearest encounters. But even weaker distant tugs can be important when the original binding to the Sun is already faint. The outer Oort cloud is already a region shaped by perturbation. Passing stars can stir it. The galactic tide, meaning the slow differential pull of the Milky Way across the solar system, can reshape long-period comet orbits over immense timescales. In that sense, the rogue planet does not introduce a new kind of physics. It introduces a new and moving source of the same kind of influence. What changes is the local strength and geometry of the pull. A nearby star passing the solar system might disturb one broad sector of the cloud over time. A rogue planet moving through the cloud from within the Sun's extended sphere of influence adds a more concentrated and more mobile disturbance. Many bodies in this region are so weakly bound that their long-term fate is uncertain, even before the rogue planet arrives. Their orbits balance between remaining attached to the Sun and being lifted away by later encounters. For such objects, the rogue planet can act as a deciding force. Some are pulled onto slightly more secure solar orbits. More are likely to be destabilized, because the region is so loosely held that added motion often pushes bodies toward escape or toward radically reshaped long ellipses. There is no reason to imagine a clean sorting process. The cloud responds statistically, with a growing spread of orbital outcomes rather than a simple pattern. From far away, the outer structure of the cloud also becomes less symmetrical. Before disturbance, the Oort cloud is often described as roughly spherical, though no one sees it directly as a complete mapped shell. That ideal shape is only an average picture. In reality, the distribution is irregular, and any major passage through it adds further asymmetry. A rogue planet passing through one sector creates a local scar in orbital distribution. Some regions are depleted as objects are ejected. Some are stirred into new inclinations. Some become future source regions for long-period comets. The cloud remains vast, but it is no longer as dynamically quiet as before. If astronomers in the inner solar system could observe the process with perfect knowledge, they would still not see immediate spectacle. The distances are too large, the objects too faint, and the timescales too extended. The main evidence would lie in calculations. Precise orbital models would begin to show that some distant bodies no longer move as expected. The pattern would suggest a perturber, which is a body whose gravity alters the motion of others. Yet in practice, most individual outer Oort objects are too dim and too distant to track directly. So the disturbance begins largely unseen. It is a real restructuring of the solar system's outermost reservoir, but one that unfolds in darkness and sparse data. Collisions between Oort cloud bodies remain improbable during this stage. The region is too diffuse. Even when orbits are altered, the chances of direct impact between icy nuclei are still low. The important product of the disturbance is not debris from collision, but changed orbital architecture. Paths that were once quiet and remote become paths with new perihelia, meaning new closest distances to the Sun, or with new energies that allow escape. Some objects receive only a slight adjustment and continue on vast loops. Some are detached from old routes and sent into different long-term evolutions. The cloud begins to exchange members with interstellar space more actively than before. The rogue planet itself also feels the effect of the Sun during this passage, but in the outer Oort region its own path is still only gently curved. It remains primarily an intruder crossing a weak outer domain. The individual icy bodies do little to affect it in return. Their masses are too small and too scattered. The flow of influence is almost entirely one way. The rogue planet reshapes the cloud, while the cloud offers almost no resistance. So in this second region, the event becomes measurable not by visible destruction, but by the loss of stillness in one of the solar system's most remote populations, the outer Oort cloud. Once governed mainly by the Sun, galactic tides, and occasional stellar passages, now acquires a new moving source of order and disorder at once. Some icy bodies are unbound. Some are redirected. Some are placed on different million-year journeys around the Sun. The great distant sphere remains dark, cold, and sparse. But its old balance has begun to shift. As the rogue planet continues through the remote outer reservoir, the first large consequence of its passage becomes clearer in dynamical terms. The distant Oort cloud is not only a storage region of icy remnants, It is also the source of many long-period comets, which are comets that take more than 200 years to orbit the Sun and often far longer. Their paths are shaped by weak binding, extreme distance, and sensitivity to outside disturbance. When the rogue planet rewrites a portion of this cloud, it does not produce a single stream of inward objects. It creates a broad redistribution of orbital possibilities. Some bodies are lifted away from the Sun forever. Some are shifted onto different distant loops. A smaller fraction are sent inward. This inward delivery is important because it is the first pathway by which a disturbance in the far outer solar system can eventually become visible closer to the Sun. Yet even here the process is slow. A comet newly redirected from the outer cloud does not arrive in the planetary region within days or years. It may still require thousands, tens of thousands, or much longer to fall inward, depending on the exact shape of its revised orbit. The rogue planet therefore acts less like a sudden trigger and more like a long gravitational editor. It changes the starting conditions from which future comets emerge. Each icy body in the disturbed region receives its own new trajectory. Some gain energy and move on to more extended orbits, barely attached to the Sun or no longer attached at all. Others lose energy relative to the Sun and begin to fall inward on steeper ellipses. An ellipse is a stretched orbit with the Sun away from the center. In the Oort cloud, such ellipses can become extremely elongated, with one end still at immense distances and the other aimed far deeper into the solar system. What determines the outcome is geometry. The precise direction of the rogue planet's motion, its mass, its speed, and the location of each icy body together decide whether a given object is thrown outward, tipped aside, or drawn onto an inward route. The result is not a neat shell of incoming comets, but a distorted and anisotropic response. Anisotropic means uneven by direction. One sector of the Oort cloud may produce a future excess of incoming long-period comets, while another sector may be depleted. Some objects that were once likely to remain remote for millions of years now acquire paths that bring them far closer to the Sun. Others that might have become comets in a more ordinary future are instead removed from the system. The rogue planet does not simply increase comet activity everywhere. It redistributes which comets the solar system will receive and from where. At this stage, the disturbed objects are still mostly dark icy nuclei. They are not yet active comets in the familiar sense. A comet becomes visibly active when sunlight warms its surface enough for frozen volatile substances to turn directly from solid to gas. That gas drags dust outward, forming a coma, which is a surrounding cloud and often a tail. In the distant outer regions now under discussion, the Sun remains too weak to create those features. The objects are still frozen travelers. Their significance lies in their altered motion, not in their appearance. For observers in the inner solar system, the first strong evidence of change may still not come from direct detection of the rogue planet itself. Instead, it may emerge from statistics gathered over long periods. Astronomers track the arrival directions, orbital energies, and inclinations of newly discovered long-period comets. If enough distant bodies have been perturbed, the pattern of incoming comets may begin to deviate from expectation. A mild excess from a particular broad region of the sky might appear. The distribution of perihelia, the points of closest approach to the Sun, might shift. Certain classes of weakly bound comets could become more common. None of this would be instant or obvious. It would build gradually, and careful modelling would be required to separate the signal from the natural background of comet delivery, already caused by galactic tides and past stellar encounters. This means the rewritten comet paths are both a physical and an informational change. Physically, the solar system begins receiving different future trajectories from its outer reservoir. Informationally, those trajectories carry clues about a hidden perturber. In planetary science, unseen masses are often inferred through the motions they impose on visible bodies. That is how Neptune was predicted in the 19th century from irregularities in Uranus's orbit, and the same logic applies here in a looser and more difficult context. The Oort cloud is harder to observe than the known planets, and its members are much fainter and more numerous, but the principle remains the same. Motion reveals mass. Not every perturbed body becomes a threat to the inner solar system. Many new trajectories still keep their closest approach far outside the planetary region. Some objects pass closer to the Sun than before, but remain beyond Neptune or even beyond the main Kuiper Belt. Some enter orbit so long that, although they are now technically inward bound, their actual arrival lies far beyond any human timescale. The cloud is so vast that the early outcome is dominated by long delays. The rewriting of paths is immediate in a dynamical sense, but delayed in every visible sense. Even so, the importance of this stage is profound. The solar system's future impact environment begins changing here, at the level of altered source populations. Long-period comets are especially difficult objects because their orbits can arrive from almost any direction, and at high speeds relative to the planets. Their unpredictable nature is built into their origin. A rogue planet passing through the distant cloud does not instantly send a storm toward Earth, but it increases the complexity and uncertainty of the solar system's future comet traffic. The precise scale of that increase depends on mass and trajectory. A smaller rogue world would stir only a limited volume. A larger one, especially a gas giant mass, could perturb a wider share of the cloud and change the future supply more strongly. There is also a second effect. Some disturbed icy bodies may interact later with one another only indirectly, through shared changes in orbital space, as new long ellipses overlap regions they previously avoided. The population becomes dynamically hotter, meaning more spread in speed and direction. Actual collisions remain rare because the space is still enormous, but the distribution of orbital elements grows broader and less settled. The outer solar system becomes less like a quiet archive and more like a system processing delayed consequences. The rogue planet itself continues inward, while this invisible rewriting spreads behind it. It leaves not a wake of light, but a wake of altered futures. Millions or billions of icy bodies do not move together, yet enough of them receive changed paths that the solar system's outer memory is no longer the same. The Oort cloud had been a distant record of early planetary scattering and later galactic influence. Now it also becomes a record of passage. The first major outcome of the intruding world is not impact, capture, or visual spectacle. It is the redirection of countless small icy bodies onto new long journeys, some away from the sun, some back toward it, and many into paths that will only reveal their new meaning after ages of travel. Beyond Neptune lies a broad transitional region where many icy bodies no longer follow the relatively regular pattern of the major planets. This is the scattered disk, a population of distant objects on elongated, tilted, and often unstable paths shaped mainly by the past and continuing influence of Neptune. Unlike the nearly spherical Oort cloud, the scattered disk is more strongly tied to the flat architecture of the planetary system. Its objects still belong to the outer solar system in a more immediate way. They are closer, more tightly bound to the Sun, and more directly connected to the giant planets. When the rogue planet enters this region, it begins to move from a distant gravitational disturbance into a more structured and dynamically active environment. The scattered disk is not dense in the ordinary sense. distances between bodies remain enormous. Yet compared with the Oort cloud, it is a much richer field of interaction. More objects are known here. Their orbits are better constrained. Their relation to Neptune matters constantly. Some are lifted far out at aphelion, the most distant point from the Sun, and return inward again on long loops. Some cross or approach Neptune's orbital domain. Some remain in temporary resonances, which are repeating gravitational patterns where orbital periods line up in simple ratios. This means the rogue planet enters a region already shaped by dynamical tension. Its effect here is again gravitational, but the character of that effect changes. In the Oort cloud, the main result is the rewriting of very weakly bound distant trajectories over immense timescales. In the scattered disk, the rogue planet acts on bodies that are both closer to the Sun and more strongly linked to the giant planets. Small changes now have a clearer path toward wider consequences. A disturbed scattered disk object can become more strongly Neptune crossing. It can be shifted into a new resonance or pushed out of an old one. It can be detached, meaning placed on an orbit whose closest approach stays too far from Neptune for strong future interaction. It can also be thrown inward in a way that eventually feeds populations closer to the planets. This region contains many bodies that are already dynamically active in the long-term sense. Their orbits are not fixed for the age of the solar system. They diffuse, scatter, and occasionally migrate between categories. Some become centaurs, which are icy bodies with unstable orbits crossing or approaching the giant planets. Some later become short-period comets after repeated gravitational shaping by the outer planets. The rogue planet therefore enters a region that functions as a transfer zone. It is not only a storage reservoir, it is a channel through which outer icy matter can move inward over time. A passing rogue planet broadens that channel and scrambles its structure. Objects near its path receive the strongest perturbations, their orbital eccentricity, which measures how stretched an orbit is, may rise or fall. Their inclinations may increase, tipping them farther from the main planetary plane, or in some cases decrease. Their longitudes, arguments, and other orbital angles shift. These changes sound abstract, but together they determine whether a body remains in a distant long-term orbit, begins crossing Neptune more often, or is launched toward the inner giant planet region. The scattered disk responds not as a cloud of collisions, but as a web of altered orbital relationships. Because the rogue planet is now closer to the established planetary system, the question of timescale also changes. Many of the modified bodies still evolve slowly, but their new paths can begin interacting with Neptune and the other giant planets more readily than disturbed Oort cloud comets can. The solar system starts to develop a second delayed response. The first response was the long-term rewriting of distant comet supply. The second is the more active reworking of a region already capable of delivering unstable icy bodies inward. This does not produce immediate catastrophe. It produces a growing excess of pathways by which instability can propagate. Neptune remains the key local organizer of this zone. Much of the scattered disk exists because Neptune long ago flung icy planetesimals outward during the early migration of the giant planets. Even today, Neptune continues to sculpt the region through repeated distant encounters and resonant control. As the rogue planet enters, it effectively becomes a second sculptor, but an unplanned and mobile one. Some objects that would once have been guided mainly by Neptune now respond to two competing influences. A resonance that had preserved relative stability may weaken or break. A body that would have remained detached may be sent back into stronger contact with Neptune. Another may be lifted away from Neptune's reach altogether. This makes the region less coherent. Patterns that once reflected the long accumulated history of Neptune's influence begin to blur. Astronomers studying the distant solar system often look for clustering gaps and preferred orbital alignments to infer the past actions of the giant planets or of unseen perturbers. A rogue planet entering the scattered disk would add fresh structure, but it would be irregular and path-dependent. In one sector, orbital inclinations might fan out. In another, semi-major axes, the characteristic sizes of orbits might spread into new ranges. Elsewhere, a resonance population could thin out as bodies are extracted or destabilized. The once slow and somewhat comprehensible map of outer body dynamics becomes more mixed. Direct collisions are still uncommon. Even in the scattered disk, space remains too vast for collision to dominate. But collision probabilities do rise slightly over long periods when orbits are stirred into more crossing configurations. More important than collision itself is the production of future unstable populations. Some scattered disk objects become centaurs more efficiently under this disturbance. Centaurs are transient bodies, often ice-rich, moving among the giant planets on chaotic timescales much shorter than the age of the solar system. They are important because they can evolve further inward and because their motion is especially sensitive to repeated planetary encounters. The rogue planet does not need to reach the inner planets to begin shaping their distant future. It only needs to increase the supply of bodies entering the unstable giant planet corridor. From the inner solar system, this stage might eventually become more detectable than the earlier Oort cloud response. Known trans-Neptunian objects could begin showing distributions that no longer fit existing models. New discoveries might reveal unusual clustering or fresh scattering signatures. Yet even here, human observation would struggle. The objects are dim, the orbits long, and the baseline for certainty demanding. Astronomers would probably first notice statistical oddities rather than a dramatic visual sign. A growing suspicion of a substantial external perturber would strengthen, but full interpretation would remain difficult until the rogue planet came closer or more objects betrayed its influence. The passage through the scattered disk therefore marks a transition. The rogue planet is no longer merely stirring the farthest and faintest outer reservoir. It is now interfering with a region that feeds the active dynamical machinery of the outer planetary system. The changes remain quiet and mostly invisible, but they are less remote in consequence. Icy bodies are detached, redirected, or sent into more unstable states. Neptune's long stewardship of the region is no longer singular. The outer solar system begins to lose some of its previous orbital memory and gain a new one written by intrusion. In this colder borderland beyond the giant planets, the architecture of slow instability becomes broader, less ordered, and more open to inward transmission. The Kuiper Belt forms the broad outer rim of the known planetary system. It lies beyond Neptune and contains countless icy bodies left from the solar system's formation, including dwarf planets, smaller frozen worlds, and fragments too small to see except through careful observation. Unlike the distant Oort cloud, this region is more strongly flattened into the general plane of planetary motion. Unlike the scattered disk, much of it has a more recognizable structure. Some objects move on relatively moderate orbits. Some are locked into resonances with Neptune. Some belong to dynamically colder populations, meaning their paths are less tilted and less stretched. Together, these populations preserve a great deal of the outer solar system's historical order. When the rogue planet reaches this region, that order begins to loosen. The Kuiper Belt is still spacious beyond ordinary imagination. Its members are separated by immense distances, and the total mass of the belt is far smaller than that of a major planet. Yet it is dense enough in dynamical terms for patterns to matter. Resonances with Neptune maintain islands of relative stability. Groups of objects share related orbital properties. The larger dwarf planets, though only a tiny fraction of the total, serve as recognizable markers within this broader frozen landscape. Here, a rogue planet does not merely disturb weakly bound or irregular bodies. It begins interfering with one of the solar system's clearest outer structures. The first changes are again gravitational and selective. Objects nearest the rogue planet's path feel the strongest influence. Their semi-major axes, eccentricities, and inclinations change by different amounts depending on distance and geometry. Some bodies are pulled into more stretched orbits. Some are nudged into different orbital periods. Some are tilted farther from the main plane. Others are shifted enough to leave resonance with Neptune, which is often a decisive loss of protection. A resonance is a repeating relation between orbital periods that allows bodies to avoid close disruptive encounters, even while sharing broadly similar zones. When such a pattern is broken, a once stable object can become vulnerable to later scattering. This matters because the Kuiper Belt is not only a collection of ice-rich remnants, it is a map of preserved long-term relationships. The rogue planet begins erasing parts of that map. Resonant populations may thin as members are displaced. Cold classical objects, which tend to have more circular and less inclined orbits, and are thought to preserve especially old conditions, may be stirred into warmer, more chaotic states. Detached objects may be drawn into stronger interaction with Neptune or with the intruder itself. The belt ceases to be purely a fossil record and becomes an actively rewritten system. The largest dwarf planets in the outer belt respond according to the same laws but with more significance because of their mass and visibility. Pluto, Eris, Makemake, Haumea, and other large bodies are still tiny compared with the major planets, but they are massive enough to anchor families of fragments, to preserve long observational histories, and to serve as indicators of broader instability. A rogue planet passing through or near this region could alter the orbits of such worlds measurably over time. It would not necessarily eject them at once. More often, it would change the long-term balance that keeps their paths understandable. Pluto, for example, remains safe from Neptune because of a stable resonance. But if outer gravitational architecture is shifted strongly enough, the future security of such arrangements can weaken. The key idea is not immediate collision. It is loss of established orbital protection. Across the wider belt, collisions also become somewhat more likely than before, though still rare on short timescales. The Kuiper Belt today is already a collisional environment in the geological sense, meaning impacts have shaped surfaces and created families of smaller fragments over billions of years. But present-day collision rates are low because the belt is sparse. A rogue planet increases orbital crossing and velocity dispersion, meaning relative speeds and path overlap rise over long timescales. This can increase fragmentation. More debris is produced. More smaller bodies are placed on unstable paths. Dust generation may rise locally, though not enough to turn the region into a bright cloud. The dominant change remains dynamical, but collisional consequences slowly accumulate behind it. Some objects are also pushed inward out of the Kuiper Belt into Neptune crossing orbits. This is a major pathway by which the disturbance begins feeding the next inward region. Bodies that had once remained in stable distant zones can become scattered objects or centaurs after the rogue planet alters their motion. In that sense, the belt starts leaking more actively. It does not collapse, it does not empty, but it becomes less efficient at retaining the populations it once held. The clean separation between stable outer belt members and more unstable transitional objects begins to blur. The shape of the belt as a whole can also change. Astronomers often describe the Kuiper Belt through subpopulations because its structure contains information about the history of planetary migration, especially Neptune's outward movement in the early solar system. A rogue planet introduces a second major sculpting force after that formative era. Depending on its mass and trajectory, it may create fresh asymmetries, new clusters, or broad depletion zones. One side of the belt could become more dynamically heated than another. Certain semi-major axis ranges may lose occupants. Inclination distributions may spread. A population once tightly linked to Neptune's resonances may become more diffuse and harder to classify. Future astronomers would read this altered belt differently from the one known before the intrusion. The rogue planet itself still experiences only limited braking. Passing through the Kuiper Belt does not slow it much. The total mass of the belt is too low, and direct encounters with large bodies remain uncommon. So although the belt suffers disturbance, it does not significantly capture or tame the intruder. The flow of influence remains mainly one way. The rogue planet changes the belt. The belt records the passage but does not determine the rogue planet's fate. Observation now becomes easier in principle than in the earlier sections, because many Kuiper Belt objects are known and tracked. If a large rogue planet were entering this region, astronomers might detect unexpected orbital drift among trans-Neptunian bodies, unusual resonant behavior, or fresh populations of destabilized objects. The intruder itself, if large, warm, or reflective enough, might also become a target of direct searches. But even with modern surveys, certainty would take time. Outer solar system dynamics are slow, and many small bodies are still undiscovered. The first scientific picture would likely emerge as a mismatch between prediction and observation, followed by increasingly persuasive evidence of a new massive perturber. In this fifth region, then, the solar system's frozen outer edge loses some of its long-preserved order. The Kuiper Belt is no longer only a distant archive of formation and migration. It becomes a live response surface to an incoming world. Resonances weaken or break. Cold populations are stirred. Dwarf planets drift onto revised futures. Collisions become slightly more likely over immense spans. More bodies leak inward toward Neptune's wider domain. The belt still remains recognizably there, still broad and icy and dark under weak sunlight. But it is no longer the same structure. Its old arrangement begins to give way under the pull of a world that was never part of its design. Neptune rules the outermost true planetary domain of the solar system. Beyond it lie reservoirs, belts, and scattered populations. But Neptune is the first of the major planets to stand as a dominant local mass in the path inward. Its orbit marks a transition from distant icy structure to the established architecture of the giant planets. Here the rogue planet no longer moves only through populations of small bodies shaped by the planets. It begins to move into the direct gravitational sphere of a planet itself. A sphere of influence is the region around a body where its gravity becomes the main local control over nearby motion, even though the Sun remains dominant overall. For Neptune, that sphere is large enough to govern moons, temporary captures, close encounters, and many of the detailed orbital changes of trans-Neptunian objects that come near it. The rogue planet does not need to pass extremely close to Neptune for Neptune's presence to matter. Once their orbital paths approach the same broad zone, the solar system's outer dynamics become a two-body contest nested inside the Sun's larger field. From this point onward, the rogue planet is not simply crossing the outskirts. It is entering negotiation with the system's native giants. Neptune itself is a cold gas giant, rich in hydrogen, helium, and heavier volatile substances, with a deep atmosphere, a system of moons, faint rings, and a mass large enough to shape surrounding space over immense timescales. It has long acted as the main sculptor of the Kuiper Belt and scattered disk. Many outer bodies owe their present orbits to repeated distant encounters with Neptune over billions of years. When the rogue planet comes near Neptune's broad dynamical domain, the old outer solar system encounters something it has not known since the era of planetary migration, another large world able to compete with Neptune in the same neighbourhood. The exact outcome depends strongly on mass, speed, and geometry. If the rogue planet is only a few times the mass of Earth, its interaction with Neptune is serious, but not necessarily dominant in a single pass. If it is comparable to Neptune or larger, the encounter becomes much more consequential. Relative velocity also matters. A faster intruder spends less time in Neptune's effective range and is harder to redirect. A slower one allows a longer exchange of energy and momentum. The closest approach distance matters most of all. Even a moderately massive rogue world can produce large effects if the geometry brings it near Neptune's path, while a more massive one passing farther away may still impose only gradual orbital change. At this stage, the solar system begins to show planetary scale perturbation rather than only small body response. Neptune's orbit around the Sun may be altered slightly, or, in stronger cases, substantially. Its eccentricity may increase, making the orbit more stretched. Its inclination may change, tipping it farther from the original planetary plane. Its semi-major axis may shift inward or outward depending on the direction of the energy exchange. These changes need not be large in percentage terms to matter. In a tightly coupled planetary system, even modest orbital shifts in a giant planet can propagate widely through resonances and long-term instabilities. The rogue planet also changes course. A close encounter with Neptune can bend its solar trajectory more strongly than any small body population could. This does not usually amount to capture, but it can redirect the intruder, changing its perihelion distance, its inclination, or its future encounters with the other giant planets. In some cases, Neptune acts as a gravitational sling, meaning the rogue planet gains or loses orbital energy relative to the Sun through exchange with Neptune's own motion. Such interactions are familiar in spacecraft navigation, though here the masses are planetary and the effects vastly larger in consequence. Neptune can either help drive the rogue planet farther inward, or help deflect it onto a less penetrating path. Neptune's moon system would also feel the disturbance, though the details depend on how close the rogue planet comes. Triton, Neptune's largest moon, is already unusual, probably a captured Kuiper Belt object moving on a retrograde orbit, opposite Neptune's rotation. Smaller moons occupy more delicate gravitational arrangements. A distant rogue passage would mainly alter Neptune's path around the Sun while leaving the moon system broadly intact. A closer passage could inject measurable instability into outer, irregular moons, shift ring structure, or change the long-term stability of weaker satellite orbits. The rings themselves, faint and dusty, are especially sensitive to perturbation because their particles occupy narrow dynamical environments. They would not burst outward dramatically, but their pattern could be reshaped if Neptune's local gravity field and orbital context were disturbed enough. For the populations around Neptune, the effect is immediate in a dynamical sense. Resonant objects beyond Neptune may lose old protections if Neptune's orbit changes. Bodies currently near the border between stable and unstable motion can be tipped into repeated Neptune encounters. Neptune crossing populations may thicken. Detached objects can be reattached to stronger planetary influence. In other words, Neptune's own reorganizing role expands. The rogue planet does not replace Neptune as the main long-term outer sculptor, but it interrupts and modifies Neptune's control at the very source. This is also the stage at which astronomers within the inner solar system would almost certainly begin to recognize that the disturbance involves a major unseen mass, rather than only statistical oddities among comets and trans-Neptunian objects. Neptune is a known planet with a well-measured orbit. If its motion began to diverge from prediction beyond the ordinary effects of the known planets, the discrepancy would command attention. Precision astrometry, meaning exact positional measurement, would reveal something substantial. The difficulty would lie in interpreting the cause quickly enough, especially if the rogue planet remained faint or observationally awkward against the background sky. But Neptune's behavior would become a clear and load-bearing clue. What remains uncertain at this stage is how much of the interaction can occur in a single significant pass. Planetary systems are usually stable because close encounters between giant planets are rare after formation. A rogue intruder changes that assumption, but the outcome still depends on chance geometry. A direct near-Neptune encounter is not guaranteed. The rogue planet may pass through Neptune's broad region without coming particularly close, in which case the main effects are cumulative but moderate. Or it may cross at a distance small enough to alter both worlds strongly, setting up a chain of further interactions inward. Observations and simulations would indicate possible ranges, but the exact path would remain a problem of initial conditions. So the sixth region is where the event becomes unmistakably planetary, Neptune's outer domain. Once the final major frontier of the established solar system begins to feel the presence of another world with comparable gravitational seriousness. Small body reservoirs have already been stirred behind the intruder, but here the architecture itself begins to flex. Neptune's orbit may shift, resonances may fray, moons and rings may move onto subtly or substantially changed futures. Most important, the rogue planet's own path can now be redirected in ways that determine whether the encounter remains largely outer or advances more deeply into the giant planet system. In the cold blue province of Neptune, the intrusion stops being only a disturbance of debris and becomes a contest between planets. Inside Neptune's domain, the solar system still appears spacious, but the balance among the giant planets is far more delicate than the great distances suggest. Uranus occupies the next inward major orbit, and although it seems remote from Neptune on human scales, the two planets belong to a linked gravitational system. Their motions are stabilized by distance, by the Sun's dominance, and by the absence of close encounters across billions of years. This long calm is part of what gives the outer solar system its present order. When the rogue planet passes beyond Neptune's region and moves inward toward Uranus, it enters a layer where slow changes in one planet's orbit can begin spreading through the broader architecture of the giant planets themselves. Uranus is an ice giant, similar to Neptune in size and broad composition but distinct in important ways. It contains hydrogen and helium above a deeper interior rich in water, ammonia, and methane under extreme pressure. Its atmosphere is cold and comparatively subdued in visible appearance, though active processes still occur within it. Most strikingly, its rotation axis is tipped by about 98 degrees, so the planet effectively rolls around the Sun on its side. That unusual tilt likely records a major collision or sequence of collisions from the early solar system. In the present era, however, Uranus moves on a relatively regular orbit, and its moons and rings remain arranged within a stable local system. The rogue planet enters a region where that stability depends not only on Uranus itself, but on its place within the larger chain of giant planet motion. The outer giant planets do not need to collide to affect one another profoundly. Their mutual gravity acts continuously across time. Resonances, near resonances, and secular interactions all help shape their long-term behavior. A secular interaction is a slow exchange of orbital properties such as eccentricity and inclination over long timescales without the need for close repeated alignment. This means that if Neptune's orbit has already been altered, even modestly, Uranus can begin responding over time. If the rogue planet now also passes through Uranus's wider dynamical zone, the response becomes stronger and more immediate. The question is no longer whether the outer giant system remains unchanged, it is how the change is distributed among its members. The direct interaction between the rogue planet and Uranus depends, as before, on mass, speed, and closest approach. A distant pass may mainly add a slight shift to Uranus's orbit around the Sun. Its semi-major axis may move by a small amount. Its orbital eccentricity may increase. Its inclination may tilt somewhat farther from the original common plane of the planets. Because Uranus already has an extreme axial tilt, it is important to distinguish between the tilt of its spin axis and the tilt of its orbit. The rogue planet's gravity would first and most strongly affect the orbit. Changes in axial tilt are possible through torques during very close interactions, especially over long times or through shifts in satellite structure. But the orbital response is the primary effect at this stage. A closer encounter could do much more. Uranus may be nudged inward or outward relative to its old path. It may enter a different long-term gravitational relation with Neptune or Saturn. Some configurations increase orbital crossing risk over millions of years, while others remain non-crossing but more eccentric and therefore more disruptive to surrounding small body populations. Even a small percentage change in a giant planet's orbit can matter, because it changes where resonances fall and how strongly the planets exchange angular momentum, which is the rotational and orbital quantity associated with motion around a center. In simple terms, the giant planets store much of the solar system's organized motion. When one of them is moved, the rest eventually feel it. This is why Uranus's region is best understood as a layer of deep orbital balance, rather than merely the location of another planet. The rogue planet does not only encounter Uranus as an isolated world, it encounters a node in a network. If Neptune has already been perturbed and Uranus is now directly affected as well, then the outer giant pair can no longer be assumed to preserve their old mutual rhythm. The shift may remain moderate, in which case the solar system acquires a new, but still broadly stable arrangement, or it may become large enough to seed future chaos, where tiny differences in conditions grow into widely different planetary outcomes over long timescales. In celestial mechanics, chaos does not mean immediate disorder. It means that long-term prediction becomes sharply sensitive to initial details. Uranus's moon system also deserves attention here, though again only within this current region. The planet possesses large regular moons such as Titania, Oberon, Umbriel, Ariel, and Miranda, along with smaller moons and a set of narrow dark rings. A distant rogue passage would likely leave the moons bound but may alter Uranus's hill sphere, which is the region where its gravity dominates over the Sun for satellite retention. A significant change in the planet's solar orbit can shift the long-term conditions under which the moons remain stable. A closer encounter could disturb irregular outer moons first, as these are more weakly held. Ring particles, like those around Neptune, occupy delicate gravitational niches and may respond through spreading, altered confinement, or local instability. The main point is not immediate destruction. It is the weakening of long-trusted regularity. The wider effect around Uranus extends to centaurs and transitory icy bodies moving among the giant planets. This region acts as a dynamic corridor between the distant icy populations and the deeper giant planet system. If Uranus's orbit changes, the corridor changes with it. Bodies that once encountered Uranus at certain distances and frequencies now do so differently. Some are scattered onward towards Saturn and Jupiter more efficiently. Some are ejected from the solar system more readily. Some linger longer in unstable paths. The rogue planet therefore modifies not only the architecture of the giant planets, but also the flow of smaller bodies threading between them. For observers in the inner solar system, Uranus provides another strong line of evidence. Its orbit is well known, though less immediately intuitive to the public than those of the inner planets. Precision measurements over time would begin to show whether changes seen near Neptune are propagating inward. If Uranus and Neptune both depart from predicted motion in ways consistent with a single incoming mass, confidence in the rogue planet interpretation would rise sharply. Yet even then, scientists would still face uncertainty. Many possible encounter geometries can produce similar early signatures. The exact future of the system would remain difficult to calculate until the intruder's own path was constrained much better. In this seventh region, then, the solar system's disturbance deepens from local planetary encounter into system-level imbalance among the outer giants. Uranus stands not merely as the next world inward, but as part of the long mechanical memory of the planetary system. Its orbit, moons, rings, and surrounding corridor of unstable icy bodies all depend on an ancient calm that the rogue planet now disrupts. The effects may still unfold slowly, but they are no longer confined to remote debris or to a single outer planet. The old equilibrium among the far giants has begun to bend, and with that bending the giant planet system becomes less a fixed framework and more an evolving response. Saturn marks a further inward change in the solar system structure. It is still a giant planet, still far from the Sun compared with Earth, and still surrounded by broad volumes of emptiness. Yet Saturn's region feels more intricate than the domains beyond it, because it combines great mass with extraordinary fine structure. Its rings are the most elaborate visible disk of particles around any planet in the solar system. Its moon system is extensive and varied, with icy satellites, geologically active worlds, and distant irregular bodies. Its orbit also forms part of the deeper, long-term pattern, linking all 4 giant planets. When the rogue planet approaches Saturn's sphere of influence, the intrusion enters a region where delicate local systems coexist with massive gravitational control. Saturn is a gas giant made mostly of hydrogen and helium, less dense than water on average, with a broad atmosphere, a strong magnetic field, many moons, and rings composed mainly of water ice mixed with darker material. The rings are vast in width, but very thin in vertical extent. They are not solid sheets. They are collections of particles ranging from tiny grains to larger blocks, each orbiting Saturn under the combined influence of gravity, collisions, and the shaping effect of small moons. This makes Saturn's region unusually responsive to perturbation. A change in the planet's orbit or a direct external gravitational disturbance can propagate through systems that are already finely balanced. The rogue planet does not need to cut through the rings themselves to matter here. Long before any such improbable close geometry could be imagined, Saturn's motion around the Sun becomes the main concern. Like Neptune and Uranus, Saturn can exchange orbital energy and angular momentum with an incoming massive body. If the rogue planet passes through Saturn's broader dynamical neighborhood, Saturn's semi-major axis, eccentricity, and inclination may shift. Because Saturn is more massive than Uranus or Neptune, it can impose a stronger redirecting influence on the rogue planet, while also resisting change somewhat more effectively. But resistance does not mean immunity. Even modest orbital alterations in Saturn can have deep consequences because Saturn occupies a central position in the giant planet system, especially in relation to Jupiter. One of the important long-term relationships in the solar system involves the near commensurabilities, or near simple numerical ratios, among the orbital periods of the giant planets. Saturn and Jupiter in particular participate in powerful secular interactions that help organize the architecture of the solar system. If Saturn's orbit is shifted, even slightly, those long rhythm patterns are modified. The effect does not instantly break the system, but it changes how orbital elements cycle through time. A stronger or more eccentric Saturn can alter the positions of resonances in the asteroid belt and influence how Jupiter later responds to the rogue planet. In this sense, Saturn's region acts as both a local environment and a transmission point. Disturbance here does not stay here. Locally, Saturn's rings are among the most sensitive structures the rogue planet has yet approached. Their particles live in a carefully sculpted gravitational field shaped by Saturn's mass, oblateness, moons, and internal oscillations. Oblateness means that Saturn is flattened at the poles because of its rapid rotation, and this affects orbital behavior in the ring system. Small moons called shepherd moons help confine narrow rings and gaps. Resonances with larger moons create waves, edges, and divisions. If Saturn's solar orbit changes, the ring system remains bound to Saturn, but the wider gravitational environment of the whole Saturnian system adjusts. If the rogue planet comes close enough, even temporarily, it can perturb outer moons first and slightly alter the resonant balances that maintain ring sharpness and structure. The likely result is not immediate destruction, but distortion, spreading, fresh wave patterns, and long-term rearrangement. Saturn's moons provide a broader record of how deep the disturbance becomes. Titan, the largest moon, is a substantial world with a thick nitrogen atmosphere and methane-based weather cycles. Enceladus vents water-rich material from fractures near its south polar region, revealing a subsurface ocean, Iapetus, Rhea, Dione, Tethys, and many smaller moons occupy distinct orbital zones. The inner regular moons are more tightly bound and thus more protected. Distant irregular moons, moving on inclined and often retrograde orbits, are less secure. A moderate rogue passage may only perturb the outermost satellites measurably. A closer one could reorder parts of the irregular moon population, destabilize marginally bound objects, or alter the future resonances among regular moons. Once again, the most vulnerable structures lie at the edges of stability. The space around Saturn also contains a population of centaurs and transitioning icy bodies, whose future paths depend on repeated encounters with the giant planets. As the rogue planet crosses this region, it modifies those encounter statistics. Some objects that would once have remained between Uranus and Saturn for long intervals may be handed onward more rapidly. Others may be expelled outward or inward with greater efficiency. The corridor of unstable small bodies becomes more agitated, and Saturn becomes both a recipient and a transmitter of that agitation. The solar system's outer to inner conveyor of icy bodies begins moving under altered rules. A direct close encounter between Saturn and the rogue planet would be especially consequential because Saturn is massive enough to bend the rogue planet's path substantially. This could either increase or decrease the chance of deeper penetration toward Jupiter. A gravitational assist type interaction might send the rogue world onto a steeper inward path. or conversely lift its perihelion and reduce its access to the innermost planetary region. Saturn, therefore, becomes one of the last major filters before the system's most dominant planet is reached. But this filtering is not intentional or stable. It is a matter of geometry and energy exchange in a system now departing from its old balance. From the perspective of observation, Saturn's region would provide extremely strong evidence that the solar system is undergoing a planetary scale event. Saturn is bright, well measured, and closely studied. Deviations in its orbit would be easier to detect than similar changes in more remote worlds, especially once enough time had passed for the perturbation to accumulate. Changes in ring structure or in the orbits of outer moons could offer additional clues, though these would be harder to attribute uniquely at first. Still, the combination of altered giant planet motion from Neptune through Saturn would make the case overwhelming that an external massive perturber is moving inward through the system. What remains uncertain in any specific real case is the exact severity. Planetary dynamics can amplify small differences over long time scales, but not every encounter becomes catastrophic. Saturn may emerge with only modest orbital adjustments and some disturbed outer satellites, while the rogue planet continues inward. Or Saturn may be shifted enough to alter the future of resonances across the solar system for millions of years. Observations would constrain the path, and simulations would map many possible futures, but certainty would still lag behind the event itself because the system would now be highly sensitive to the precise sequence of encounters. In this eighth region, the intrusion reaches one of the solar system's most finely structured and gravitationally important domains. Saturn's rings, moons, orbital roll, and surrounding unstable small body populations all feel the stress of an incoming world. The disturbance remains mostly gravitational, not collisional, and mostly structural, not explosive. Yet the meaning of the event deepens. A region famous for delicacy now sits inside a system undergoing large-scale rebalancing. The rings continue to circle, the moons remain in motion, and Saturn still shines with pale reflected sunlight. But the quiet mathematical order that supports this beauty is beginning to strain. Jupiter is the gravitational engine of the solar system outside the Sun. It is the most massive planet by far, containing more mass than all the other planets combined, and its influence reaches across a wide range of orbital space. In the earlier outer regions, the rogue planet disturbs reservoirs of small icy bodies and alters the paths of the giant planets that shape the outskirts. In Jupiter's region, the scale of consequence changes again. Here the incoming world encounters the strongest planetary gravitational field available short of the Sun itself. The larger outcome of the entire intrusion now depends heavily on what happens in this meeting of masses. Jupiter is a gas giant composed mainly of hydrogen and helium, with a deep atmosphere, strong magnetic field, dozens of moons, and an enormous system of gravitational control extending through the asteroid belt, the Trojan populations, and many small body pathways that link outer and inner solar system dynamics. Its orbit around the Sun is stable on human timescales, but its long-term interactions with Saturn and the rest of the planetary system help set much of the deeper architecture of orbital motion. Because of this, Jupiter acts both as a local world and as a system-wide organizer. A major perturbation here is never confined to one region alone. When the rogue planet enters Jupiter's broader sphere of influence, the first question is not whether they collide. Direct collisions between planets remain exceedingly unlikely, because even planetary systems are mostly empty space. The real question is how closely the two bodies pass and how much energy and angular momentum they exchange. If the rogue planet is relatively low in mass and passes at a large distance, Jupiter may mainly bend its path and send it onward on a modified solar orbit. If the intruder is more massive, slower, or passes nearer, the encounter becomes decisive. Jupiter may redirect it sharply, accelerate it, decelerate it relative to the Sun, or in rare geometries help place it on a temporarily or permanently bound orbit. At the same time, Jupiter's own orbit may shift enough to alter the future of the entire solar system. This encounter can be understood as a gravitational scattering event. Scattering means that two bodies pass close enough for their paths to change significantly through mutual gravity without touching. In such an event, the exact outcome depends strongly on the approach angle and relative motion. A rogue planet passing behind Jupiter, relative to Jupiter's orbital motion, can gain energy and leave on a faster solar trajectory. Passing in front can lose energy relative to the Sun and fall deeper inward. Jupiter itself, because it is so massive, changes less than a smaller planet would, but change there can still matter enormously. A small increase in Jupiter's orbital eccentricity, a slight shift in semi-major axis, or a modest change in inclination can move resonances across wide parts of the solar system. Jupiter's resonances are among the most powerful orbital patterns outside the Sun's direct dominance. In the asteroid belt, they carve gaps where repeated gravitational forcing makes certain orbits unstable. Among Trojan asteroids near Jupiter's orbit, they help maintain long-lived swarms sharing the planet's path around the Sun. In the broader giant planet system, Jupiter's rhythm with Saturn helps define secular cycles that reach inward toward Mars and outward toward Neptune. If Jupiter is shifted, these resonances shift with it. The solar system's machinery does not stop, but its operating pattern changes. Locally, Jupiter's moon system records the strength of any close approach. The four largest moons, Io, Europa, Ganymede, and Callisto, are massive enough and tightly enough bound to remain secure through moderate external perturbation. They are locked into a highly structured dynamical arrangement, especially the resonance linking Io, Europa, and Ganymede. Smaller inner moons are also strongly held. The most fragile members are the distant irregular moons, many of which are probably captured bodies occupying inclined and eccentric paths far from Jupiter. A rogue passage that remains distant may do little more than alter some of these outer satellites slightly. A closer one could strip part of the irregular population away, destabilize weakly bound moons, or reshape the long-term distribution of satellite orbits. Jupiter's faint rings, maintained by dust from small moons, would also respond to changes in the local gravitational environment, though they would remain far less visually dominant than Saturn's. The atmosphere of Jupiter itself remains largely unaffected in a direct physical sense, unless an encounter becomes implausibly close. The rogue planet does not stir the clouds by contact. What changes is motion through space, not weather in the ordinary short-term meaning. Yet over time, if Jupiter's orbit becomes more eccentric or tilted, the solar energy it receives through a Jovian year would change somewhat, and the broader environment of its moons could shift. These are secondary effects. The primary event is orbital. The wider significance of Jupiter lies in how it governs the flow of smaller bodies. Jupiter acts at times like a shield and at times like a source of hazard. It ejects many comets and asteroids from the solar system through gravitational encounters, reducing the long-term number of bodies that can threaten the inner planets. But it also redirects some objects inward and creates resonant pathways that can send material toward Mars and Earth. A rogue planet entering Jupiter's region therefore modifies the main gatekeeper of impact traffic. If Jupiter's orbit changes, the future delivery of asteroids and comets throughout the inner solar system changes with it. If the rogue planet itself scatters populations while passing nearby, the short and medium-term supply of unstable bodies can rise sharply. This is also the stage at which the rogue planet's own fate becomes most sensitive to a single encounter. Jupiter is massive enough to eject the intruder from the solar system if the geometry allows a sufficient gain in energy relative to the Sun. It can also throw the rogue planet into a tighter inward plunge. In a rarer case, a complex sequence involving Jupiter and Saturn together could leave the rogue body on a highly elongated bound orbit around the Sun. Such a capture is not the default expectation, but Jupiter makes it more plausible than any previous planet could because it offers the strongest planetary gravitational exchange available. The solar system is now close enough to the centre, and the masses are now large enough, that the final state begins to branch into genuinely different possibilities. For observers on Earth, Jupiter's involvement would be unmistakable. Its orbit is measured with high precision. Its moons are tracked closely. Its role in orbital calculations is central. Any significant change in Jupiter's motion would immediately transform scientific understanding of the event. At that point, the rogue planet would no longer be an inferred cause from remote anomalies alone. The system's dominant planet would be visibly participating in the disturbance, and models of future planetary stability would become urgent. The uncertainty would remain large, but the seriousness of the intrusion would no longer be abstract. In this ninth region, the event reaches the solar system's most powerful planetary pivot. Jupiter is not merely another world along the inward path, it is the place where the larger outcome is most likely decided. The rogue planet encounters the greatest available planetary mass, the strongest planetary resonances, the most effective small-body gatekeeper, and a moon system broad enough to reveal the depth of disturbance. Whether the intruder is turned away, driven inward, or set onto a rarer bound path now depends heavily on this giant encounter. In Jupiter's domain, the solar system answers the intrusion with its greatest planetary force. Between Jupiter and Mars lies the main asteroid belt, a broad population of rocky and metal-rich bodies that never formed into a full planet. Its existence reflects the early history of the solar system, especially the strong gravitational influence of Jupiter, which helped prevent planetary growth from completing in that region. The belt is not a crowded field of tumbling stones close together. It is a vast volume of space containing many objects separated by long distances. Yet despite this spaciousness, it has a highly structured internal order. Families of asteroids share common origins from ancient collisions. Gaps appear where repeated resonances with Jupiter make certain orbits unstable. The belt is both a leftover building zone and a carefully carved dynamical system. When the rogue planet's disturbance reaches this region, either through changes in Jupiter's orbit, through the shifting resonant pattern of the giant planets, or through the rogue planet's own continued inward path, the asteroid belt begins to lose some of that carved order. This is the first major rocky debris region affected after the giant planet corridor. Unlike the icy outer populations, the asteroid belt contains bodies made more often of silicate rock, metal, carbon-rich material, and remnants altered by heating and collisions in the early solar system. The nature of the material is different, but the governing process remains gravitational. The belt is reordered first through changed orbits, and only later through any secondary increase in impacts. The most important structures in the asteroid belt are its resonances. Certain orbital periods line up with Jupiter in simple numerical ratios, and these repeated tugs gradually remove bodies from particular zones. These are the Kirkwood gaps. places where asteroids are underrepresented because resonant forcing can drive their eccentricities upward until they move onto planet-crossing or otherwise unstable paths. Saturn also contributes through more subtle long-term interactions, and the combined resonant web across the belt is intricate. If Jupiter's orbit changes even modestly, the locations and strengths of these unstable zones change with it. The belt does not simply shake, its mathematical boundaries are rewritten. A shifted Jupiter means that some asteroids now find themselves in stronger resonance than before, while others leave old resonances behind. New pathways open toward instability. Asteroid families that once occupied relatively secure zones can be exposed to repeated forcing. Bodies in previously marginal orbits can be driven toward greater eccentricity, meaning their paths become more elongated and begin crossing those of Mars or even Earth over time. Inclinations may also change, lifting more asteroids out of the belt's usual flattened structure. The overall result is a rise in dynamical excitation, which means a broader spread in orbital shapes and directions. This excitation has two linked consequences. First, more asteroids move onto unstable or crossing paths. Second, relative speeds among some asteroids increase, which affects collisions inside the belt itself. Collisions in the asteroid belt are not new. Over billions of years they have shattered larger parent bodies and produced many asteroid families. But in the present-day belt, the collisional environment is relatively quiet compared with its early history. A major new perturbation changes that balance. More crossing orbits mean somewhat greater impact probability over long timescales, and higher collision speeds make impacts more efficient at fragmentation. Large asteroids are still unlikely to strike one another often, but smaller-scale breakups and cratering events become more common than before. As breakups increase, the belt produces more fragments. Some remain near the parent family. Some drift under sunlight-driven effects over long timescales and later enter resonances. Others are directly launched into more unstable solar orbits. This creates a delayed multiplication of hazard. The rogue planet does not need to pass through the belt physically to make the belt more active. By altering Jupiter and the resonant pattern, it can turn a relatively ordered debris population into a richer source of future planet-crossing objects. The belt becomes not only more disordered but more productive of inward-moving rock. The belt is also diverse in composition and location. Inner belt asteroids tend to differ from outer belt ones in average composition. Reflecting temperature gradients and material history from the solar system's formation, a broad dynamical disturbance does not erase these differences, but it mixes outcomes that were once more separated. Bodies from outer parts of the belt may now be sent inward along pathways once less accessible. Some may approach Mars-crossing or Earth-crossing orbits more efficiently. The inner solar system begins to receive not just a greater number of unstable objects, but a somewhat altered sample of material sources. Large asteroids and dwarf planets within the belt act as local records of the disturbance. Ceres, the largest body in the asteroid belt and the only dwarf planet there, is massive enough to influence nearby smaller bodies, but far too small to resist major changes in the surrounding resonant environment. Vesta, Pallas, and Hygeia, along with other large asteroids, would likely remain bound on altered but intact orbits unless the rogue planet's intrusion had become exceptionally deep and violent. The more realistic effect is not immediate ejection of these major bodies. It is the gradual placement of their neighborhoods into a more unstable regime. Family members can diffuse outward from old boundaries. Collision fragments may become more mobile. Stable gaps and clusters may shift their shape. If the rogue planet itself approaches the belt directly, the effect becomes stronger and more localized. Its gravity can scatter asteroids individually. opening depletion lanes along its path and sending selected bodies into new, high eccentricity trajectories. A direct crossing would still not resemble a billiard table sweep through crowded rubble. The belt is too sparse for that, but over time, a substantial mass passing through could leave behind a very clear dynamical scar, new asymmetries, unusual inclinations, broadened family distributions, and a sudden increase in injected Mars-crossing and Earth-approaching asteroids. The belt would then record not only a shifted resonant framework from Jupiter, but also a direct passage signature from the intruder. For scientists observing from Earth, this stage would be deeply concerning because the asteroid belt is much better mapped than the distant Oort cloud or even the Kuiper Belt. Changes in orbital distributions could be tracked more directly. A rise in the number of newly unstable asteroids would not remain abstract. Surveys would begin finding more objects on unusual trajectories. Resonant escape routes into the inner solar system would become more heavily populated. Models of impact hazard would need continual revision as the belt adjusted to its new gravitational environment. This does not mean the belt instantly turns into a storm of impacts. The timescales remain mixed. Some effects would begin quickly in orbital terms, while many actual arrivals into the inner solar system would unfold over centuries, millennia, and longer. But the source conditions would have changed. The main rocky reservoir between Jupiter and Mars would no longer be operating under the old architecture that had governed it for ages. Its internal order, already shaped by collision and resonance, would become more unstable, more fragmented, and more efficient at delivering debris inward. In this 10th region, the intrusion reaches the solar system's principal rocky debris field. The asteroid belt is not destroyed, but it is reordered. Resonances shift, gaps move, families spread, collisions become somewhat more common. New fragments are produced, and more bodies begin the long transition from belt member to planet crosser. The disturbance that began in distant icy darkness has now crossed into the realm of stone and metal. The solar system's middle debris zone starts to change from a carved archive of past formation into an active source of future impacts. Inside the asteroid belt, the solar system changes character again. The broad outer reservoirs of ice and the giant planet domains give way to a region where the planets are smaller, denser, and more closely tied to the history of rocky formation near the Sun. Mars stands at the outer edge of this inner planetary system. It is a terrestrial planet, meaning a world built mainly of rock and metal rather than thick layers of hydrogen and helium. Its orbit lies close enough to the asteroid belt that any major change in the belt structure quickly matters here. When the rogue planet's disturbance crosses inward to this region, the most immediate consequence is not yet direct planetary encounter. It is the transformation of Mars's orbital environment and the widening of unstable pathways between rocky debris and rocky worlds. Mars today moves on a somewhat eccentric orbit compared with Earth, and its gravitational reach is much smaller than that of the giant planets. Yet it plays an important role in the inner solar system because it sits beside the asteroid belt and serves as the first major planetary filter for many rocky bodies leaving that reservoir. Numerous near-Mars asteroids already exist, and some pathways into the inner solar system pass through Mars crossing stages. If the asteroid belt has been dynamically heated by changes in Jupiter and by possible direct scattering from the rogue planet, then Mars becomes the first inner planet to feel a substantial rise in incoming traffic. This change begins with orbital overlap. More asteroids acquire paths whose perihelia or aphelia now intersect Mars's orbit. Some do so only briefly before later encounters move them elsewhere. Others spend extended periods as Mars crossers, repeatedly passing near the planet over many orbits. A close pass with Mars can redirect an asteroid, sometimes ejecting it from a Mars-crossing path, and sometimes moving it inward toward Earth-crossing space. Because Mars is much less massive than Jupiter, its scattering power is weaker, but that weakness has its own effect. Objects are not cleared as efficiently. They can linger through many encounters, creating a more prolonged and complex transition population between the belt and the deeper inner solar system. This means the disturbance now begins to concentrate in a narrower region, instead of a broad belt-wide rise in instability. There is a growing stream of bodies threading through Mars's neighborhood. Some are large enough to remain individually important. Many more are modest in size. Their composition varies, reflecting the mixed material of the belt, from more rocky inner belt types to darker carbon-rich bodies from farther out. The key change is statistical. Mars's local environment becomes busier, less predictable, and more collision-prone than before. Mars itself may also respond orbitally if the rogue planet's disturbance has significantly altered the architecture of the giant planets. The inner planets are not isolated from the outer ones. Secular interactions carry slow exchanges of eccentricity and inclination through the whole planetary system. If Jupiter's orbit changes, Mars is especially sensitive because it lies closest to the giant planet domain, and because its own orbit is already somewhat elongated. Over long timescales, even moderate changes in Jupiter can produce measurable shifts in Martian orbital behavior. Mars may become slightly more eccentric, slightly more inclined, or more variable through time. None of this requires the rogue planet to come physically near Mars. The larger system can transmit the effect inward. This matters because Mars's own gravitational environment includes two small moons, Phobos and Deimos, both likely captured or reworked remnants from the planet's past. They orbit close to Mars compared with the scales under discussion, so they are not the first structures to respond to distant planetary rearrangement. But if Mars's orbit changes over time, the broader solar context of the Martian system changes with it. More important than its moons is the planet's role as a target. A more excited asteroid population means a higher long-term chance of impacts on Mars. The planet's thin atmosphere provides far less shielding against incoming objects than Earth's thicker air, so smaller bodies can reach the surface more easily. New craters would accumulate at an elevated rate if the disturbed environment persisted. The immediate physical state of Mars, however, does not transform simply because more asteroids cross its path. Its deserts remain cold and dry. Its polar caps continue their seasonal growth and retreat. Its surface pressure remains low. The disturbance is orbital and probabilistic. It changes the frequency of encounters, not the planet's visible appearance from one day to the next, but across centuries, millennia, and longer. The record would become clear. A region once governed by relatively settled impact rates and known orbital pathways would become more active. Mars would begin to register the inward transmission of a disturbance that started far beyond Neptune. There is also a broader population in this zone often called the near-Earth object pathway, though at this stage it is more accurate to think of it as the outer inner solar system pathway. Asteroids and some dormant comet-like bodies that leave the main belt often pass through Mars-crossing states before reaching or approaching Earth. A rogue planet disturbance strengthens this conveyor. More objects are fed into transitional orbits. Some are removed quickly through collision with the Sun, ejection, or planetary scattering. Others survive long enough to move still farther inward. Mars therefore acts as both recipient and distributor. It absorbs some of the increased hazard and passes some of it on. If the rogue planet itself remains on a path that carries it no farther inward than Jupiter or the asteroid belt, This region may still become one of the most important practical consequences for rocky planets. A rogue planet does not need to enter the inner solar system directly to raise future impact risk here. It only needs to alter the giant planet architecture enough to destabilize the main source reservoirs of rock and ice. In many scenarios, the lasting humanly relevant consequence would be less a dramatic near-Earth passage of the rogue world and more an enduring increase in the number of hazardous bodies delivered toward the terrestrial planets. At the same time, uncertainty remains high in the details. Planetary systems transmit disturbance through many overlapping resonances and secular patterns, and small differences in the outer encounter sequence can lead to different inner outcomes. Some configurations may leave Mars only modestly affected, with a noticeable but not overwhelming rise in crossing asteroids. Others may drive long intervals of enhanced bombardment and stronger orbital variability. What is known from celestial mechanics is the direction of change. Greater instability in the asteroid belt and in Jupiter's orbit tends to propagate inward, and Mars is the first rocky world positioned to receive that propagation. In this 11th region, then, the disturbance crosses the threshold from debris fields and giant planets into the orbital environment of the terrestrial worlds. Mars stands at that threshold. Around it, the traffic of unstable rocky bodies grows heavier. Planet-crossing paths become more common. Long-term impact rates can rise. The orbital influence of the altered giant planets begins to reach into the inner solar system with greater force. The red planet remains outwardly itself, still circling the sun in thin, cold sunlight, but the space through which it moves is no longer as orderly as before. The disturbance has now entered the realm where worlds of rock begin to live under its consequences. Earth moves within a narrow and valuable band of orbital stability. Its path around the Sun is close to circular, its axial tilt is moderate, and the combination of these features helps produce the long-term balance of seasons, surface temperatures, and climate rhythms under which its oceans remain liquid. This stability is not absolute. Over geological timescales, Earth's orbit and tilt vary slightly through gravitational interactions with the other planets, especially Jupiter and Saturn. These cycles are small enough that the planet remains habitable, but large enough to shape ice ages and long climate trends. When the rogue planet's disturbance reaches Earth's orbital environment, the first question is therefore not only whether Earth itself is struck or displaced, it is whether the quiet orbital conditions that support long continuity begin to shift. By the time the disturbance arrives here, the solar system has already been altered in several linked ways. The outer reservoirs of icy bodies have been stirred. The giant planets have experienced changed trajectories or changed gravitational relations. The asteroid belt has begun releasing more unstable rock. Mars's neighborhood has become a more active passage zone. Earth now sits deeper inside the system, exposed not just to one incoming world, but to the accumulated consequences of all those earlier changes. Its local environment is no longer defined only by the known planets and the usual background of near-Earth objects. It becomes part of a larger field of rebalanced motion. Earth's orbit can be affected in two main ways. The first is indirect, through the altered gravitational behavior of the giant planets. If Jupiter's or Saturn's orbit has shifted even modestly, the long-term secular forcing on Earth changes. Earth may develop slightly greater orbital eccentricity, changing the contrast between its nearest and farthest points from the Sun over the course of a year. Its inclination may vary somewhat relative to the solar system's mean plane. The rate at which its orbital ellipse precesses, meaning slowly rotates through space, can also change. These shifts need not be large to matter. Small orbital differences can alter seasonal distribution of sunlight, intensify or soften climatic cycles, and change the long-term pacing of glaciation and warming. The second pathway is more direct. If the rogue planet itself penetrates this far inward, Earth's orbit can be perturbed by its own gravity during a closer solar system passage. The effect depends entirely on geometry. A distant pass might produce only a slight modification in Earth's orbital elements, measurable but not catastrophic. A nearer pass could alter the semi-major axis enough to move Earth to a somewhat different average solar distance. It could increase eccentricity more strongly, creating greater seasonal asymmetry. It could tilt the orbital plane relative to the rest of the planetary system. Such changes would not need to eject Earth from the habitable zone to have major consequences. Even within the broad region where liquid water remains possible, climate patterns could shift substantially if the orbit became more elongated or less stable. Alongside orbital change comes a second major concern: increased flux of near-Earth objects. The phrase near-Earth object refers to asteroids and comets whose orbits bring them near Earth's path around the Sun. Earth already lives with a background population of such bodies, many tracked, many still undiscovered at smaller sizes. The earlier sections of the disturbance have already increased the pathways by which asteroids leave the main belt and by which some long-period comets are redirected inward. By the time the disturbance reaches Earth's region, the background population of hazardous trajectories can rise. This rise may begin gradually and continue for extended spans. It does not imply continuous impacts, but it does imply a busier orbital neighborhood and a higher long-term probability of major impacts. Comets remain especially important because they can arrive from many directions and at high relative speeds. Asteroids are often easier to track over repeated passages, while long-period comets can emerge on trajectories with less warning. If the rogue planet has significantly disturbed the Oort cloud and the scattered populations beyond Neptune, then Earth's future impact environment acquires more uncertainty from that outer source. At the same time, destabilized asteroids from the Belt and Mars crossing corridor can create a more sustained inner hazard. Earth thus faces a combined effect: a possible change in its own orbit and a likely increase in the complexity and frequency of threatening nearby objects. The local planetary neighborhood also includes Venus and Mars on either side and the Moon in close companionship, though the Moon belongs more properly to the next inward layer of this story. For Earth's broader orbital environment, the key point is that the spacing and resonant relations among the terrestrial planets may no longer remain exactly as before. The inner planets are usually stable because they occupy non-crossing or weakly interacting orbits under the Sun's dominance. But their long-term evolution is not perfectly rigid. If the giant planets have been shifted, and if an additional massive perturber passes through, then the secular architecture of the terrestrial planets can be modified. Earth's orbital eccentricity and inclination are not fixed constants. They are outcomes of a moving many-body balance. The atmosphere does not directly shield Earth from orbital disturbance, but it changes how some consequences are felt. A thicker atmosphere than Mars means smaller incoming objects can burn up before reaching the ground, reducing the hazard from lesser debris. Yet the atmosphere also couples tightly to climate. If Earth's orbital pattern changes, the atmosphere and oceans respond. A slightly more eccentric orbit changes how solar energy is distributed across the year. Stronger precession cycles alter which hemisphere experiences stronger seasonal contrasts at perihelion, the closest point to the Sun. Over long spans, ice cover, rainfall belts, and ocean circulation would adjust. The disturbance in this section is therefore not only celestial, it reaches the environment of the surface through the chain of orbit, sunlight, and climate. What remains uncertain is the scale. Earth is not automatically doomed by a rogue planet entering the solar system. The most likely severe consequences in many plausible scenarios arise from indirect destabilization and increased impact risk rather than from a direct near-pass by the rogue world itself. If the rogue planet is redirected or ejected by Jupiter or the Sun before entering the terrestrial zone, Earth may still inherit a more hazardous debris environment and altered long-term forcing from the changed giant planets. If the rogue planet comes close, the consequences become more immediate and potentially more profound. But such closeness is not the default in every inward crossing scenario. Orbital mechanics allows many outcomes, and only some are extreme for Earth itself. For observers on Earth, this is the stage at which the event becomes personal in a planetary sense. What was once a matter of remote celestial structure now begins to affect the orbit of the homeworld and the character of the space around it. Precision measurements would reveal if Earth's orbital elements were shifting beyond known natural patterns. Near-Earth object surveys would begin recording a changed statistical background. Impact risk assessments would grow more urgent. Climate models would need to account not only for atmospheric and geophysical processes, but for a newly altered orbital forcing from the wider solar system. In this 12th region, Earth's orbital environment becomes measurably strained. The steady path that supports familiar seasons may change in subtle or stronger ways. The surrounding population of hazardous asteroids and comets may grow more active. The inner planetary system remains bound to the Sun, but its old regularity weakens. Earth still circles in sunlight, still turns with its known day and night, still carries its atmosphere and oceans, but the space through which it moves has become less settled. The disturbance has now reached the conditions that define the planet's long continuity. The Earth-Moon system is a paired structure within the inner solar system, and its stability depends on both local gravity and the larger motion of the Earth around the Sun. The Moon is not merely a nearby companion. It is a substantial satellite, unusually large relative to its planet, and its presence affects tides, axial stability, and the long evolution of Earth's rotation. When the rogue planet's disturbance reaches this level, the focus narrows from Earth's broad orbital environment to the specific geometry of this familiar two-body system. The question is no longer only how Earth moves around the Sun, but how Earth and Moon continue moving around one another while together passing through a changed solar system. The Moon orbits Earth at an average distance of about 384,000 kilometers, while the Earth-Moon pair together orbit the Sun. More precisely, both bodies orbit a common centre of mass called the barycenter, though because Earth is much more massive, that point usually lies inside Earth itself. This means the Moon is both a local companion and part of a larger solar orbit. In ordinary times, the arrangement is stable. The Moon slowly drifts outward by a few centimeters per year, because tidal interaction transfers rotational energy from Earth's spin into the Moon's orbital motion. Earth's rotation slows very gradually, and the lunar month lengthens over immense timescales. These are quiet, measurable processes. A rogue planet disturbance does not erase them, but it can superimpose stronger gravitational stress from outside. The first way this happens is indirect. If Earth's solar orbit changes, then the Earth-Moon system moves through a somewhat different external gravitational environment. A slightly more eccentric Earth orbit changes the Sun's tidal influence on the Moon over the course of the year. A change in Earth's inclination or orbital precession alters the geometry through which the Moon's orbit evolves. These effects are usually modest, but the Moon's orbit is already subject to many overlapping perturbations from the Sun. It is not a perfect circle and not fixed in space. Its orbital plane tilts, precesses and responds to long gravitational cycles. If the solar system's larger architecture is disturbed, the patterns governing lunar motion also shift. The second way is more direct. If the rogue planet comes into the terrestrial region closely enough, its gravity can perturb the Earth-Moon system as a unit and, depending on distance, also differentially affect Earth and Moon. Differential means that the pull is not exactly the same on both bodies because they are separated in space. This is the basis of tidal force. A distant external body pulls both Earth and Moon almost equally, and mainly changes their shared solar orbit. A closer one exerts a noticeably different pull on each, and that can alter the size, shape, or orientation of the Moon's orbit around Earth. The critical question becomes distance, very far away. The rogue planet only adds a small correction. Closer in, it can excite the lunar orbit measurably. An excited lunar orbit may become more eccentric, meaning the distance between Earth and Moon would vary more strongly from one point in the orbit to another. Its inclination relative to Earth's equator or to the ecliptic, the main plane of planetary motion, may change. The line of nodes, where the Moon's orbital plane crosses the ecliptic, may precess differently. These sound like mathematical details, but they translate into real physical consequences. Eclipses would follow different long-term cycles. Tidal patterns would be modified. The long-term stabilizing influence the Moon exerts on Earth's axial tilt could weaken, or at least operate differently if the lunar orbit were significantly altered. Earth's obliquity, or axial tilt, is unusually stable for a terrestrial planet because the Moon exerts a torque that helps prevent chaotic tilting under the influence of the Sun and planets. Mars, which lacks a comparably large Moon, experiences much larger obliquity variations over long timescales. Earth does vary, but within a relatively narrow range. If the Moon's orbit were shifted strongly enough, that stabilizing effect could change. The likely outcome in many realistic scenarios would still be a modified but bound Moon, not an immediate loss of axial control. Yet even moderate weakening of lunar stabilization could matter over long spans, because Earth's climate depends not only on its orbit, but also on the steadiness of its spin axis. Tides are the most immediate physical link between Earth and Moon. Ocean tides arise mainly from the Moon's gravity, with a substantial contribution from the Sun. If the Moon moves into a different orbit, tidal amplitude and timing change. A slightly higher eccentricity would increase the contrast between stronger and weaker tides across the month. A changed orbital distance would alter average tidal strength. A modified inclination would shift the latitudinal pattern of tidal forcing. Coastal systems, ocean mixing, and some long-term biological rhythms tied to tides would all respond. These changes would not happen because the oceans suddenly behave differently on their own, but because the Moon's pull is part of their regular forcing. There are more severe possibilities, though they require a closer rogue planet encounter. If the external perturbation is strong enough, the Moon's orbit could in principle be driven into a much larger eccentricity, moved farther outward, or in extreme cases destabilized. Destabilized does not automatically mean ejected. It can mean an orbit made more vulnerable to later chaotic evolution, or one that crosses thresholds for long-term instability. Complete removal of the Moon from Earth's control would require a very substantial perturbation, and is not the ordinary expectation unless the rogue planet passes unusually near. Collision between Earth and Moon also remains highly improbable, except in extremely extreme scenarios. The more scientifically grounded expectation is alteration, not immediate destruction. The Moon itself would also record the disturbance on its own surface environment, though not through atmosphere or weather, because it has neither a substantial atmosphere nor active hydrology. Its tides are solid body tides, slight internal flexing caused by gravitational forces. A changed orbit could alter that flexing. Its pattern of Earthrise in the lunar sky would change only if the orbital geometry changed significantly. More important than any surface visual effect is the Moon's dynamical role within the Earth system. It acts as a gravitational partner. If that partnership is modified, Earth's future rotational and climatic behavior changes with it. For observers on Earth, this stage would be deeply unsettling because the Moon is a direct and visible part of the sky. Astronomers would measure changes in its orbit precisely through laser ranging, which already tracks the Moon's distance to very high accuracy using reflectors left on its surface. Even small deviations from expected motion would be detected. Tidal predictions would begin to require correction. Eclipse cycles would drift from their old patterns. What had once been one of the best measured natural systems would begin to reveal the pressure of the wider celestial disturbance in unmistakable terms. In this 13th region, the intrusion reaches the most intimate orbital structure Earth possesses. The Earth-Moon system remains bound in many plausible scenarios, but its geometry may no longer be the same. The lunar orbit can be perturbed. Tides can change. Earth's long-term axial stability may be modified. The familiar relation between planet and satellite continues, yet under a new external stress. The disturbance that began in interstellar darkness has now entered the gravitational bond between Earth and Moon, turning even this ancient partnership into part of the solar system's broader rebalancing. Closer to the Sun, the inner planetary system becomes more compressed. Orbital periods shorten, speeds increase. The space between one planet's path and another remains vast by human standards. Yet in dynamical terms, the region is crowded compared with the outer solar system. Venus and Mercury move through this dense inner field under the strongest sustained solar gravity any planet experiences. Their motions are already shaped by subtle relativistic effects, by long secular interactions with the other planets, and by the fact that small orbital changes near the Sun can have large long-term consequences. When the rogue planet's disturbance reaches this region, the solar system enters its most compact planetary layer before the Sun itself. Venus is the nearer of the two major inner targets in this section. It is often called Earth's sister planet because of its similar size and mass. But its actual state is very different. A dense carbon dioxide atmosphere, global cloud layers rich in sulfur compounds, and an extreme greenhouse effect keep its surface at temperatures hot enough to melt lead. Venus rotates slowly and in a retrograde direction, meaning opposite to the rotation of most planets. Despite these unusual local conditions, its orbit around the Sun is relatively circular and dynamically important to the inner system. Small changes in Venus's motion matter because Venus is massive enough to affect Earth and Mercury over long timescales. If the rogue planet or the altered giant planet system transmits disturbance this far inward, Venus may experience changes in semi-major axis, eccentricity, inclination, and apsidal precession, which is the slow rotation of the line connecting nearest and farthest points in its orbit. These changes need not be large to matter. Venus's present low eccentricity helps maintain a very steady solar energy input over the course of its year. A more elongated orbit would change how much sunlight it receives at different points. Because Venus already has an extremely dense atmosphere, the immediate climatic significance would differ from Earth's, but the orbital significance for the inner system would still be substantial. A shifted Venus alters the gravitational background through which Earth and Mercury move. Mercury lies still closer to the Sun, and occupies the most precarious major planetary orbit in the solar system. It is small, dense, and only weakly protected by its own gravity against outside perturbation compared with larger planets. Its orbit is already the most eccentric among the major planets, and the most strongly influenced by the Sun's deep gravitational well. General relativity, the modern theory of gravity developed by Einstein, becomes especially noticeable in Mercury's orbital precession, meaning the point of closest approach to the Sun advances slightly differently than classical gravity alone would predict. In ordinary times, Mercury remains stable on very long but not unlimited timescales. Numerical studies of the solar system show that Mercury's orbit is the most vulnerable to chaotic growth in eccentricity under certain resonant conditions, even without any rogue planet present. This makes Mercury especially sensitive to a disturbed planetary architecture. If Jupiter's orbit has shifted and the secular frequencies of the whole system are altered, Mercury can respond disproportionately. Its eccentricity may grow. Its inclination may vary more strongly. In some long-term scenarios, Mercury's orbit could become much more elongated, bringing it closer to the Sun at perihelion and farther outward at aphelion. This matters because an increasingly eccentric Mercury has greater potential to approach Venus more closely, and through that approach to pass disturbance onward into the rest of the terrestrial system. Mercury does not need to be directly approached by the rogue planet to become one of the most unstable consequences of the broader rebalancing. The reason small changes matter more here is that inner orbits are fast and closely packed. Near the Sun, a slight shift in orbital frequency can change how resonances and near resonances accumulate over long spans. The planets do not need to enter a simple resonance to become vulnerable. Secular resonances, involving matches in slow precession rates rather than orbital periods, can transfer eccentricity and inclination efficiently. Mercury is especially exposed to this kind of effect. Venus, because of its greater mass and more circular orbit, is generally more robust. But even it can become part of a strengthened chain of coupling if Mercury's motion grows wilder. A direct rogue planet passage into this region would make the situation more severe, though such deep penetration is not required for inner instability to grow. If the rogue planet comes near Venus's orbital zone, Venus could be moved onto a more eccentric or inclined path, with consequences for Earth's future secular forcing. If it enters Mercury's zone, the innermost planet could be scattered strongly because its orbital speed is high, but its gravitational influence is modest. Close encounters remain unlikely in exact collision terms, but the compactness of the region means that gravitational scattering now operates in a tighter field where the Sun's pull dominates every motion. A perturbation here can rapidly change whether a planet remains on a non-crossing path. Mercury and Venus themselves would not undergo immediate surface transformation from orbital change alone, at least not in the short term. Mercury remains airless and heavily cratered, with extreme temperature contrast between day and night driven by its slow rotation and proximity to the Sun. Venus remains wrapped in dense cloud and crushing heat, but over longer times, changed orbits alter solar input and tidal conditions. Mercury in a more eccentric orbit would experience even stronger variation in solar heating. Venus, in a more stretched orbit, would see somewhat larger annual changes in received sunlight, though its massive atmosphere would distribute heat efficiently. Still, the most important effects here are orbital, not meteorological. The Sun's role also becomes more dominant in this section. Closer in, every perturbation must compete with the Sun's strong gravity. That strength can stabilize motion by keeping planets tightly bound, but it also means that once eccentricity rises enough, consequences become severe. A planet with a much more elongated orbit near the Sun experiences stronger velocity, changes between perihelion and aphelion, and may cross critical dynamical thresholds more readily. In the innermost system, there is less room for error. A configuration that would remain comfortably separated in the outer solar system can become risky here because the orbital lanes are compressed. From the point of view of observation, Venus and Mercury would provide different signs. Venus is bright and easier to monitor in detail from Earth and from spacecraft. Mercury is harder to observe because it stays close to the Sun in the sky. Yet its orbit is measured with great precision through radar and spacecraft tracking. If either planet began departing from predicted secular behavior, scientists would understand that the disturbance had reached the deepest planetary core of the system short of the Sun itself. Mercury, especially, would become a warning sign because of its known long-term sensitivity to chaotic excitation. In this 14th region, the rogue planet's disturbance reaches the crowded inner lanes of Venus and Mercury, where solar gravity is intense and long-term stability is more fragile than it appears. Venus may carry altered forcing into the terrestrial system. Mercury may respond with amplified orbital instability. The closer one moves to the Sun, the smaller the tolerances become. The planets still circle in their ancient light, but the mathematical spacing that has kept them apart for ages now bears the pressure of a changed system. In the tight inner field before the Sun, even modest disturbance can become consequential. At the center of the solar system, the Sun remains the dominant mass, the source of almost all light and the anchor of every planetary orbit. All earlier disturbances, whether in the Oort cloud, among the giant planets, within the asteroid belt, or across the terrestrial worlds, ultimately unfold inside the Sun's gravitational field. The Sun does not sit outside the event as a passive lamp. It is the central body around which the entire outcome is decided. By the time the rogue planet reaches this innermost region, the question becomes final in a dynamical sense. Does the intruding world leave the solar system, remain bound to it, strike the Sun, or pass through on a transformed path that forces the whole system into a new long-term arrangement? The Sun is a main sequence star powered by nuclear fusion in its core. Where hydrogen is converted into helium under immense temperature and pressure, its visible surface is only the outer layer from which light escapes. Above it lie the chromosphere and corona, thin hot layers extending outward into space, while the solar wind carries charged particles through the planetary system. Yet for the motion of a rogue planet, the most important solar property is neither radiation nor plasma. It is mass. The Sun contains about 99.8% of the mass of the solar system. This means that every planetary encounter inward has taken place within a field overwhelmingly controlled by the Sun, and any final state must be understood first as an orbit around, away from, or into this star. If the rogue planet reaches the inner solar system after encounters with Jupiter, Saturn, or the terrestrial planets, its trajectory by then may differ greatly from the one on which it first entered from interstellar space. It may still remain on a hyperbolic path, meaning an unbound orbit that carries it back out of the solar system after one passage. It may have lost enough energy through gravitational exchange to become bound on a long, highly elongated ellipse around the Sun. It may, in principle, be directed onto a path that intersects the Sun itself, though that requires a very particular geometry and is not the most likely outcome. What the Sun provides is the central well of gravitational potential. Whether the rogue planet escapes, remains, or is destroyed depends on how much orbital energy it retains while moving through that well. A direct impact on the Sun is possible in principle, but difficult in practice. Space near the Sun is still mostly empty, An incoming orbit must be aimed with unusual precision to intersect the solar disk rather than merely pass through perihelion and swing away again. If a rogue planet did strike the Sun, the event would release a vast amount of gravitational energy as the planet accelerated inward, but the Sun would not be destroyed. The planet's mass, unless it were itself near stellar scale, would be tiny compared with the Sun's. The star would absorb the material, likely producing a temporary disturbance in its outer layers and a local injection of heavy elements and angular momentum, but the Sun's overall structure and fusion process would remain essentially intact. For the rest of the solar system, the more important issue would be the prior chain of perturbations already left behind before impact. Much more likely than impact is passage near the Sun followed by a new outbound orbit. If the rogue planet remains unbound, the Sun bends its path into a strong curve and sends it outward again. In that case, the long-term consequence for the solar system depends on what happened during the inward and outward passage. The rogue planet leaves, but the changed comet reservoirs, altered giant planet orbits, shifted resonances, and disturbed terrestrial forcing remain. The system does not return to its old state merely because the intruder departs. Orbital mechanics has memory. Once angular momentum and energy have been redistributed among the planets and small bodies, the new configuration continues under its own rules. Permanent capture is less common but scientifically possible. For this to happen, the rogue planet must lose enough energy relative to the Sun during planetary encounters, most plausibly with Jupiter, or through a complex sequence among several planets, that its path closes into an ellipse. Such a captured orbit would probably not be circular or gentle. It would more likely be highly eccentric, perhaps highly inclined, and potentially very disruptive if it crossed the domains of existing planets. A captured rogue planet on a wide elongated orbit could continue disturbing the solar system for millions or billions of years, especially if its perihelion remained near the giant planets or the asteroid belt. If, on the other hand, it were captured onto a distant stable orbit with limited planetary crossing, the system might slowly settle into a new but still dynamically coherent arrangement. Observations and simulations would indicate which of these outcomes was more likely for a given trajectory, but no simple rule guarantees peaceful capture. There is also the possibility of temporary capture. In this case, the rogue planet becomes bound for a limited period, perhaps thousands or millions of years, before later encounters eject it again. Temporary capture is easier than permanent capture, because it demands only that the body enter a loosely bound state, not one stable against all future perturbations. This intermediate outcome would still matter greatly. A temporarily captured planet could continue seeding instability long after its original arrival, repeatedly perturbing outer reservoirs or crossing the giant planet zone before final departure. For the Sun itself, the rogue planet's closest approach would have little direct physical effect unless the pass were extremely near. Sunlight and the solar wind do not provide meaningful braking for a planet-sized body on such a timescale. Tidal effects from the Sun would increase at small perihelion distances and could matter for a loosely held gas giant atmosphere or for the internal stress of an icy or rocky world. But complete tidal disruption of a planet requires very close approach. In most cases, the Sun acts primarily as the central gravitational master, not as a destructive furnace pulling the rogue world apart at first contact. The more lasting issue is the final system state after the Sun has done its part and the rogue planet's path is resolved. If the intruder escapes, the solar system may still remain stable in a broad sense, yet with altered outer planet orbits, a more active impact environment, and modified secular cycles among the inner planets. If the intruder is captured, the system now contains an additional planet on whatever orbit the encounters have assigned to it. That new member could deepen instability or settle into a difficult but long-lived coexistence. If the intruder strikes the Sun, its direct presence ends, but its passage still survives in the rearranged architecture of the planets and small body reservoirs. In every case, the Sun remains central not because it prevents change, but because all change must finally be measured against solar binding. Over very long times, the solar system always seeks dynamical pathways consistent with conservation laws. Energy and angular momentum are exchanged, not lost without cause. This does not mean the result is orderly in a human sense. It means the final arrangement, however altered, still follows the same celestial mechanics that govern the system before intrusion. Some planets may occupy slightly shifted orbits. Some resonances may be stronger or weaker. Small body populations may be more depleted in one region and richer in unstable members in another. The old solar system may not survive in its previous exact form, but a new one emerges from the same laws. In this 15th and innermost region, the story reaches the only place where every orbit is ultimately decided. The Sun does not react with spectacle visible across the galaxy. It continues to shine, to fuse hydrogen, and to hold the system together as best a central star can while masses around it exchange motion. The rogue planet either leaves, remains, or falls into the star. The solar system either settles into a changed stability or carries forward a deeper instability written into its revised architecture. At the center, the final answer is not drama, but orbital outcome. Under the Sun's gravity, the intrusion ends by becoming part of the system's long memory. The solar system then becomes quiet again, though not in the same way as before. The disturbance passes inward through darkness, ice, gas, stone, and sunlight, leaving each region altered according to its own structure. The outermost cloud no longer holds the same distant balance. The icy belts beyond Neptune carry new gaps, new dispersions, and new unstable paths. The giant planets continue in motion, but their old relationships may be slightly or deeply changed. Resonances shift. Small bodies inherit new routes. The asteroid belt releases more of its long-held fragments. The inner planets continue circling the Sun under a revised pattern of influence. Earth remains only one part of that broader mechanical whole. Its orbit may still be nearly familiar, or it may have grown less steady. The Moon may still rise in a similar rhythm, or in one made subtly different by outside force. The seas continue moving under gravity. The atmosphere continues to turn in sunlight. Seasons continue, though perhaps under altered timing or contrast. Nothing in the system escapes physics, and nothing in the system stands entirely apart from the changes distributed through it. Yet the same laws that allow disturbance also allow settlement. Gravity does not end when the rogue planet leaves, or when it is captured, or when it falls into the Sun. Gravity continues. The planets keep exchanging influence in slow measures. The smallest bodies keep recording old encounters in their paths. The Sun remains at the center, holding the system through every revised orbit. Over long ages, the new arrangement becomes the ordinary one. A rogue planet entering the solar system does not simply add one more world. It changes relationships, it changes timing, it changes which futures become more likely. In the end, the event is written not in noise or flame, but in motion carried forward. The system goes on, altered, still circling, still settling, still bound to its star.